Okay, so we went through an example to discuss the rules for identifying whether a vertex is articulation point or not. So the rule is this: if the vertex is classified as so first of all you need to run depth first search starting from any vertex. So we typically start depth first search from the lower ID vertex. So after you run depth first search, you identify the tree edges and the back edges. And if a vertex n is getting classified as a leaf node, then it is not an articulation point. So again, remember the definition of articulation point. If the vertex is removed from the graph should get disconnected in order to call the vertex as an articulation point. So you can always cross check once you decide whether a vertex is articulation point or not an articulation point. We just remove that vertex and just make sure what you decided is right. If the graph gets disconnected and you decided that it's an articulation point, yes, it is right. If the graph does not get disconnected, then the vertex is not an articulation point. Alright, so leaf nodes are not articulation points. Then for the root node, if it has at least two child nodes, means you should have at least two tree edges down to some child nodes, then the root node is an articulation point. Now for any intermediate vertex, the rule is this. So it may have some one or more subtrees. Now you should check from each subtree whether you have a back edge that goes above the vertex in the depth first search tree. Now if there is at least one back edge from each subtree that goes above that vertex, then the vertex is not an articulation point. But even if there is one vertex, one subtree from which there is either no back edge, or even if there's a back edge that comes only up to that vertex, there's no back edge that goes above that vertex, then that vertex is an articulation point. So presence of even one such subtree is sufficient to classify the vertex as an articulation point. So we did one example last time. Let us go through one more example. So this is the result of depth first search from the previous. We went through a couple of examples in our example cases to run depth first search. So we ran depth first search on this graph. So this is the same graph you're now looking at. So you should be able to classify the edges as tree edges and back edges. Now we started depth first search from vertex 1. So draw the depth first search tree in the top down fashion. So you have it like this. From 1 you have a tree edge to 2, and then that's only tree edge connected to 1. So then and with 2 you have 2 tree edges connected to it. So 4 and 7, and from 4 you have a tree edge to 3, and from 3 you have to 5, and then to 6, and then the back edges. So this is a depth first search tree starting from vertex 1. So now we should be able to classify the nodes. So 6 and 7 are the leaf nodes because they don't have anything further down. So leaf nodes are not articulation points. So 6 and 7 are not articulation points. Now for the root node 1, it has only one tree edge connected to it. So the rule for an articulation point for the root node is it should have at least two tree edges connected to it. So in this case you have only one. So that means the root node is also not an articulation point. Now for any intermediate vertex you have to check the subtrees. So for in the case of 2, it has two tree edges, so it has two subtrees, one subtree involving this 4, 3, 5, 6, and another subtree involving just this vertex 7. Now the one with vertex 7, from that subtree you have a back edge that goes above vertex 2 in the depth first search tree. So now let us check this subtree starting from vertex 4. Now again from this subtree you have actually the three back edges associated with this subtree. Now, two of the back edges go only up to vertex 4, but there's at least one back edge, this back edge that goes from 3 to 1. So, this back edge goes above 3, sorry, above 2 in this depth first search tree. So, the presence of this back edge between 3 and 1 is sufficient enough for this subtree. So, there are two subtrees. From each of which there is at least one back edge that goes above 2. So 2 is not an articulation point. Again, you can cross check. If you remove 2 and all these 3 edges associated with 2, 7 is still connected to the rest of the vertices through this back edge. Then these 4 vertices also connected to the rest of the vertices through this back edge that goes from 3 to 1. So that is why 2 is not an articulation point. Now similarly you can check for 4, there is only one subtree attached to 4. So from this subtree you have this back edge again between 3 and 1 that goes above 4. So because of that 4 is not an articulation point. Similarly for vertex 3 there is one subtree and there is one back edge that goes above 3. Actually there are two back edges, one between 5 and 4 and one between 6 and 4. Both the back edges go above 3. So 3 is not an articulation point. Now in the case of 5, you have one subtree just involving 6, and there is one back edge that goes from 6 to something above 5. So again 5 is not an articulation point. So basically in this graph none of the vertices are articulation points. So there is a special name if no vertex in a graph is an articulation point and the graph is connected. So what I mean by connected again, so when you run depth first search starting from some vertex like say 1, you could visit all the vertices. So if you could accomplish that, then the graph is said to be a connected graph. So and then after running depth first search you get the depth first search tree and decide whether any vertex is an articulation point or not. So if no vertex in a connected graph is an articulation point, then the graph is said to be a biconnected graph. So now a very formal definition of a biconnected graph is this: there are at least two vertices joint path between any two vertices. So in this graph that we just looked at here, you just pick up any two vertices in this graph, you could find at least two vertex joint paths. So what I mean by vertex joint paths, so between say 1 and 2, there is a path, just the edge between 1 and 2, it can itself be called a path between 1 and 2. Now you also have path 1, 7, 2. Now you have some more, you could also go 1, 3, 4, 2 and so on. Now, so the property is there should be at least two vertices joint paths. So between 1 and 2 you have one path and then 1, 7, 2. So when you say vertex is joined, there is no common intermediate vertex. So 7 is an intermediate vertex in this path, but there is no intermediate vertex in this path. So these two can be called vertexes joined. Let us say this 1, 6. So between 1 and 6 you have at least two vertexes joint paths, which are say 1, 2, 4, 6 and then 1, 3, 5, 6. So the intermediate vertices 3 and 5 are not part of this path, which is 2 and 4, so and they are not part of here. So the intermediate vertices are present in just one path and no two paths are the same intermediate vertex, then such paths are called vertexes joint paths. So in a biconnected graph you are guaranteed to have at least two vertexes joint paths. So how can we decide whether a graph has at least two vertexes joint paths? Just run depth first search and check if any vertex is an articulation point or not. So if the graph is connected, means all vertices are reachable to each other and there are no articulation points in the graph, then the graph is said to be a biconnected graph. That means that such a graph will have at least two vertexes joint paths between any two vertices. So that's what we can think about as an application of what is the use of finding whether vertex is an articulation point or not. So I have one more example. You can again run depth first search, say starting from 1. Again, you should be familiar with depth first search by now, but let us just quickly go over this example. So start from 1, so you will push 1 to the stack, and then choose one of the neighbors of 1 to go further. So we'll again pick the lower ID neighbor that has not been visited yet. So we'll pick vertex 2. So the edge from between 1 and 2 can be called a tree edge. So you push 2 to the stack, and from 2 again you go further down. So again choose a neighbor, the lower ID neighbor that has not been yet visited. So among 3, 4, 5, 3 is the lower ID neighbor, so you go from 2 to 3. So you push 3 to the stack. So 3 is the third vertex to be pushed to the stack. So from 3 you could go to 5. So that's a tree edge again. So push 5 to the stack, which is the fourth vertex to be pushed to the stack. Now from 5 you could go to 2, but 2 has been already pushed to the stack. So the edge between 5 and 2 should be called a back edge, because 2 has been already visited. So we cannot call this edge as a tree edge. Then from 5 you could go to either 4 or 7. So we just break the tie by using the lower ID neighbor. So we'll go to 4. So we push 4 to the stack. Then from 4 you could go to 1, 2 and 6. So but 1 and 2 already push the stack. So we should call these edges between 4, 1 and 4, 2 as back edges. So from 4 you go to vertex 6 and push 6 to the stack. So you see all the vertices are still in the stack. You have just been pushing. You have not yet popped any vertex. So from 1 went to 2, then to 3, then to 5, then to 4, and then now to 6. So all the 6 vertices are in the stack. Now from 6 you have edge to 5, but 5 is being visited, it's already pushed to the stack. So you should call this edge between 6 and 5 as a back edge. Now from 6 you can go to 7, not visited yet, so this is called a tree edge. So push 7 to the stack. Now from 7 you have an edge to 5, which is already visited, pushed into the stack. So we should call this edge between 7 and 5 as a back edge. So from 7 we cannot go further down anywhere to a new vertex. So that's the time to pop out the vertex. So we pop out 7. So 7 is the first vertex to be popped out of the stack. So the top of the stack is now 6. So you can even write down the stack if you want to avoid making a mistake. So that you can keep track of which vertex is in the top of the stack at any time. So 6 is now in the top of the stack. Now again from 6 you cannot go anywhere else, because all the edges associated with 6 have been classified as either tree edge or back edge. So again you have to pop out 6. That's the second vertex to be popped out. So now you're back, the top of stack is 4. Now again you cannot go anywhere else, so pop out 4. That's the third vertex. Now the top of stack is 5. You cannot go again anywhere else, so pop out 5. So that's the fourth vertex. Then from 5 now your top of stack is 3. You pop out 3. So that's again now top of stack is 2. So then we cannot go anywhere else. Pop out 2. Then again we have just 1. We cannot go anywhere else. Pop out 1. So all the vertices just keep getting popped up. So now if you put together the tree edges and back edges, this is the depth first search tree we can visualize. So again we started from 1. So 1 is the root of this depth first search tree, and then we keep going down. Now again if you notice here, now we want to decide whether the vertex is articulation point or not. So let us start from the leaf node, which is just 7. There is no other leaf node, because every other node has at least one child node further down in the depth first search tree. So 7 is the only leaf node, so 7 is not an articulation point. Now in the case of the root node 1, we have only one tree edge attached to 1. So again the rule for a root node to be an articulation point is it has to have at least 2 tree edges. So in this case the root has only one tree edge associated with it, so the root node 1 is not an articulation point. Now for each intermediate vertex here you can look at the subtree. So again there's only one subtree for each intermediate vertex, because it's like a chain of vertices of the tree edges. So for 2 you have the subtree, with 3, 4, 5, 6, 7. Now from these vertices you have this back edge, so between 4 and 1, that goes above 2. So the presence of that back edge will rule out 2 to be not an articulation point. Similarly, in the case of 3, you have a subtree starting from 5, then 4, 6, 7. Now from this subtree you have several back edges that go above 3. So there's one that goes from 5 to 2, then the one that goes from 4 to 2, and then 4 to 1. So there's at least one back edge that goes above 3 from that only subtree. So 3 is also not an articulation point. Similarly, in the case of 5, there's one subtree starting with 4, then 6 and 7. There's at least one back edge that goes out from the subtree above 5. So you see there's a back edge from between 4 and 1 that goes above 5, between 4 and 2 that goes above 5. So there are two back edges that go above 5. So 5 is also not an articulation point. Now in the case of 4, there's one subtree starting from 6, and there's one back edge like this that goes above 4. Similarly, there's one back edge between 7 and 5 that goes above 4. So because of this, 4 is not an articulation point. Now in the case of 6, there's one subtree involving just 7, and there's one back edge between 7 and 5 that goes above 6. So again, because of that, 6 is not an articulation point. So none of the vertices in this graph is an articulation point. So this graph is also connected because you ran depth first search from 1 and you were able to visit all the vertices. So we can say this graph is a bi-connected graph. That means you have at least two vertices joint path between any two vertices. Okay, so let me stop and save this video. You can ask any question using a microphone or type the question.